Now we'll look at various capacitors. So here's the way to make a capacitor. Here's a conductor, an insulator, conductor, and insulator, and then you can roll this up. Okay, so this is the way to make a compact capacitor. Now, if you want to make a high voltage capacitor, these are metal plates, interleaving metal plates, and they're dipped in silicone oil because this silicone oil has a high dielectric, has a large dielectric strength. You can charge the plates to a high voltage. Okay, so here are some ways of making capacitors. Okay. Some keyboards use capacitors as detectors. So let's say in this keyboard, at the base of the key is a parallel plate capacitor. This could be a sponge material or whatever. When you press down on the key, this distance between the plate decreases. The distance between the plate decreases and the capacitance increases. So whenever you press a key, the capacitance of that capacitor increases. And all these keys are connected to 5 volts. So the capacitance of that key was, and the capacitance is given by that. All the keys are connected to 5 volts. When D decreases, when D decreases, C increases, and since they're all connected to 5 volts, charge will flow into that capacitor. Okay, so Q will increase. And that's how the computer knows which key you have pressed. Okay, so that's how some keyboards that use capacitors work. All right, so here's the Z machine. So it's a fusion reactor, test fusion reactor. So the Z machine is a controlled nuclear fusion reaction at Sandia National Labs in New Mexico. It uses a bank of capacitors connected in parallel to store 1 million joules of energy. This energy is discharged through a target. What they do is they fire lasers, and they shoot the laser at a target about 1 cc in a few nanoseconds. So they discharge all this energy through this sample in a few nanoseconds. And they heat this sample up to 2 billion degree Kelvin. Okay, so just to put that in perspective. So what we're trying to do is at the center of the sun, 4 protons will combine to form a helium nucleus. And they give us energy, plus energy. Okay. Again, anytime, so to get energy, what needs to happen is this is the ingredient, this is the product. The product needs to weigh less than the ingredient, and that's how you get energy. Now at the center, so now here's the deal. These protons are all positive, they repel each other. Okay, so they have to move extremely fast where they come close enough and the strong force takes over, and so they can form this thing. Okay. At the center of the sun, the temperature is about 15 million degree Kelvin, 15.6 into 10 to the 6. Okay, so that's the kind of temperature is needed to get the protons moving fast enough where they would combine. Okay. So about 10 million degree Kelvin. So here in this Z machine, we achieve temperatures of 2,000 million Kelvin, okay, 2 billion Kelvin. So almost 100 times greater than the center of the sun. And the reason is because at the center of the sun, the densities of protons are quite high. Here, the densities are low, so we have to heat our samples quite large temperature, so we have enough of them combining to fusing to form helium nuclei, okay, or whatever heavier nuclei. So when this million joules are discharged in a nanosecond, the power, so power is a million joules. Okay. Power is energy over time. That's a million joules divided by a nanosecond, let's say. Okay. 10 to the 15 watts. Okay. And the capacity, the power generating capacity of the world is about 10 to the 13 watts, something like that, roughly. So if you put together all the Hoover dams and all the power plants in the world. Okay, so you see, for a billionth of a second, this machine, the power output of this machine is about 100 times the combined power output of all power plants on Earth. Okay. And you can read about this thing in the on this Wikipedia page. Okay, there's another facility, Lawrence Livermore Lab in California. Here they store more energy and they discharge the energy slower. So the laser is powered by 192 power conditioning modules, each containing 300 microfarad capacitors. Okay, you can read about all of that. The capacitors are charged over a period of 90 seconds. So energy is stored in the capacitor over a period of 90 seconds. And then the laser is fired by discharging all the energy stored in the capacitors in 400 microseconds. All right, so again, in the Z machine, you store a million joules and you discharge it in a billionth of a second, in a nanosecond. In the National Ignition Facility in California, so you can go through those numbers, you're storing 330 million joules, okay, 330 times as much, except that you're discharging it much slower, 400 microseconds, almost 0.4 milliseconds, okay, so quite slowly. But anyway, the power is 1 terawatt, which is 10 to the 12 watts, okay. All right. Now we'll talk about supercapacitors and ultracapacitors. Okay, so in lots of applications, so capacitors store energy, and the energy stored in a parallel plate capacitor is 1 over CV squared. Okay. So now what you would like to do is store as much energy as possible. Now, to increase the energy storage, you can do two things. You can either increase the capacitance or increase the voltage. Now, there is a limit to the voltage, and the limit is, okay, if the electric field strength between the plates gets to be too large, you'll have a spark and the capacitor would discharge. So there's a maximum voltage you can charge a capacitor to, okay, before lightning happens between the plates. So oftentimes you don't want to go anywhere near Vmax for safety reasons. You want to try and increase the capacitance. Now, for a parallel plate capacitor, the capacitance is given by E naught A by D. A is the area of the plate, and D is the distance between the plate. Okay. So if you could figure out some way to either well, there's only so close you can bring the plates, and you don't want the plates touching and so on. So if you can figure out a way to increase the area of the plate, you can increase the capacitance. And that's the idea behind these ultra capacitors. So what they do is, so this is a parallel plate capacitor. And for an ultra capacitor, they pack this with activated charcoal, so powdered charcoal. And the effective area of the plate becomes the area of all the sum of all, the area of all the particles. So you can, if you pack a whole bunch of, let's think of sand particles, the surface area of all the sand particles becomes the effective area of the capacitor. So two layers of activated charcoal are given opposite charge and separated by an insulating material. This is the insulating material, this is the dielectric, this is activated charcoal charged negative, and this is activated charcoal charged positive. So using this, you can produce capacitors with capacitance millions of times larger than ordinary capacitors. So 5,000 farad capacitors are, you can go buy them on the internet, 5,000 farad capacitor. Okay. So however, the drawback is you can only charge them to 2 to 3 volts. Okay. And you can store energy of up to 10,000 joules. Remember, in a flash bulb cam circuit, you stored about 10 joules. So 1,000 times more energy can be stored. And here's what you can do with them. So you can have so here's a bus that runs in Shanghai on energy stored in a capacitor. Okay. All right, guys, so that finishes this chapter. Let me briefly summarize this chapter again. So what we learned in this chapter was capacitors. What do capacitors do? They can store energy, storing devices. What is their advantage? They can discharge fast. Okay. So they can give up their energy fast, and that's the whole idea. For a parallel plate capacitor, the capacitance was given in terms of their dimensions. You can take any two conductors and make a capacitor. So, and the capacitance is given by how much charge it can hold per unit volt. Okay. Capacitors store energy, and the amount of energy stored in a capacitor is CV squared. Okay. You can increase the capacitance of a capacitor by introducing a dielectric, and this guy is the dielectric constant. So here's the parallel plate capacitor. Introducing a dielectric constant between the plates increases the capacitance of the capacitor. It does other things as well, but that's the idea. Okay. All right, so those are the concepts that we learned. And I guess I'll stop now and open the floor for questions.